All right, thank you. I'm really excited to be here with all of you, and thanks for inviting me to share the work in our lab and to engage in this conversation with you all about embodied intelligence. I was going to talk a little bit about some of the explorations that we've been doing in this space. To give you some context from the point of view of our group, when we think about embodied intelligence, it's basically about how the robot's body interacts with its behavior. So a lot of very similar ideas to what you just heard. But we're very specifically interested in how does the design of the robot's body simplify its control or enable it to perform desired tasks or behaviors more efficiently. And so our group does a lot of work in computational robot design, thinking about how we can more formally think about this question, about how we can computationally think about this question. But we also think a lot about reconfigurable structures and compliance, because as you've seen over the past day and a half, the ability to change your form or the ability to be soft has a lot of impact on a robot's ability to do a certain task, to be robust, to be versatile. And so in our group, when the question of embodied intelligence is huge, right? And so that's why we have this entire conference to talk about it. But the specific question that we're trying to think about more formally in our group is how can we then tune a robot's compliance to enhance its capabilities? So this is a question that kind of has two parts. One is how do we tune a robot's compliance in the first place? And one is, well, then how do we use that to enhance its capabilities? So I wanted to illustrate our thought process through one particular example and then zoom out to think more about more general questions that I think are of interest. So to start, when we think about tuning a robot's compliance, there's a lot of work in this space. Our group in particular focuses a lot on origami-inspired approaches, where you can think about folding or thin-shelled structures, these interesting tessellated structures that have the ability to change their stiffness depending on the geometry. So one of the reasons why we're interested in these programmable stiffness origami structures is because you don't have to change the material, right? So you can change the behavior of a particular pattern by changing its geometry. And while you could do a full mechanics analysis of how that works, we've been really inspired by results from computational geometry and just geometry in general, and in particular the Bellows theorem, where there are results that tell us that the volume of a polyhedron with rigid faces is invariant under fluxing. And so what this means is that from the point of view of tuning a robot's compliance or tuning the structural components of a robot, we can really think about how we can change, how we want to change the geometry from the point of view of just how those faces in the geometry need to stretch, shear, bend kinematically in order to predict how these structures are going to change their behavior when they're put under some load. And so one of the particular designs that we've been interested in is this one you see here. It's a pretty standard Bellows design, but we can change, for example, the slope of these faces in order to change their compliance. And so you can see here one example of a folded shape that Weishi here is compressing. And even though these structures are made of thin paper, they can produce quite large reaction forces. And so by taking a look at how we can use geometry to affect stiffness, right, we can manipulate the compliance of these sorts of structures to achieve stiffnesses between something like 200 newtons per meter and 700 newtons per meter, which gives you a really large range of programmable compliance in robots. So this is just one example of something that we've been thinking about in the realm of how we can tune a robot's compliance, and then take these ideas and try to apply them to particular applications. So one interesting thing you can do now with these tunable compliance structures is you can then try to create some sort of dynamical behavior, right? And so this is an example of a jumping robot that we've designed. This is the exact same bellows pattern. And so we've just put some motors on it, added some latching mechanisms. You can see the inside of the robot is empty except for the motors. So the only thing that's providing jumping energy to this robot once the motors turn is the body itself, right? And so if these motors compress the body and then release, then you get these sorts of jumping maneuvers. And I think what's really interesting about this example is that we basically get controllable jump height for free, right? So because we can tune the stiffness of these patterns, we can tune how much energy is stored in these patterns by changing the geometry, by changing, in this case, just the angle of one of the folds. Then with the exact same controller, we can get the height that this robot jumps to change by up to 25%. And so I think this is a really nice example of how we can use the design of a robot's body in order to simplify its control. Now, this is one example where the robot jumps once and then it doesn't do anything else, right? But you can use the same idea on robots that can continuously jump and to get forward locomotion. In this case, we have the exact same idea where we have these bellows patterns at the bottom. This video is not playing. We've changed the design to carry these large loads that now we need to carry because we're using larger motors. But because these springs that we've designed are simultaneously acting as springs and dampers, we get very nice even jump heights from this robot, even when the robot is starting at different initial conditions. And so you can very nicely control the forward speed by changing the amount of compression in the springs and get these very consistent jumping behaviors, even with very simple controllers. In this case, we're just using a standard Gribber style controller. And so because these designs are compliant, then they're also able to work in a lot of different environments. So this is the exact same design where now the student has set up an obstacle course, and you can see that the robot's able to jump over these different environments. It does change its behavior though, right? And so here it slows down when it's on this egg crate area, it's faster when it's on this flat ground. And so even though we were able to get this robot designed and it's working, there are interesting questions as to, I think, how do we think about the capabilities of robots? So we've shown that you can take these designs, you can create springs of different stiffnesses, you can implement them in robots, but then how do we think about how that affects the robot's performance? So from the point of view of then robot design, then we think about it like this. The robot itself is basically your mechanical controller, right? These are the structural elements of your robot. And there's some sort of behavior that your robot is trying to achieve. And these two are linked through whatever motor control you put onto that robot. The mechanical controller is then interacting with your external environment, and this gives you mechanical feedback, right? And all of these elements together combine together to give you your robot's physical motion, right? So these are the dynamical equations you might normally use to describe your robot's trajectory or whatever it's doing in your 3D space, which gives you some sort of performance metric. If you want to be really careful about it, then the robot's body and the environment also feedback to behavioral requirements, right? So if your robot has a different kinematic structure or a different shape, then your motor control needs to change. But what we're really concerned about is, well, what goes on in here, right? Because normally the way we think about it from a mechanical engineering point of view is we choose parts, we choose mechanical properties, we choose geometries, kinematics, and then somehow an engineer takes all that information, they combine it into a design. And if you want to be more formal about it, then you can say, well, okay, let's describe a robot using a graph. Those of you who are familiar with URDFs do that a lot, probably. You can say, well, let's try to describe a task and an environment. And at the end of the day, our goal is some objective F, right? And if we want to, we can write down an optimization problem that we can use to solve for what this robot needs to look like in order to solve, or in order to optimize this objective F. But the question, I think, is what is this F, right? Because it's not entirely clear. And we've seen a lot of potential objectives that we might want for robots. In the case that I just showed you, the objective was just forward motion, but there were a lot of underlying objectives too, like reducing the amount of energy consumption, reducing how much computation, maybe increasing stability. And so it's not always entirely clear what this F is for the goal of something like embodied intelligence, right? There's similar ideas in some other applications, so I'll just show you two. Here is another pattern that we've been looking at, which has these similar ideas where when you compress the pattern, it changes its volume. It has some sort of stiffness associated with it. So when you release the pattern, it returns back to its natural shape. And because the internal volume is changing, when you put this robot in the water, it'll propel itself forward. In this case, the behavior of the robot really depends on the interaction between the robot and the environment. And yes, again, there's an objective of forward motion, but there are other objectives of cost of transport, volume of design, right? How well we can move forward versus steer left and right, right? There, and in general, the question of, well, how much do we want to put in our controller in order to get this robot to stably follow a path versus how much can we put into the robot's mechanical body become really interesting questions. Similarly, we're thinking about self-assembly. So in this case, if we have a certain pattern and we want to apply some sort of global signal to it, in this case, I'm just dropping it in hot water, then the system will self-fold, right? And the configuration that this pattern folds into is going to be different depending on whatever the external forces are. In this case, the pattern can fold into two very similar shapes, and the system is very symmetric, so it's difficult to differentiate between them. But you can figure out how to bias the pattern to fold into a particular shape more reliably. And in this case, your objective might be how often you fold into a particular shape, what is your probability of success, right? But there are also questions of, well, then if you want to reconfigure later, how do we deal with that sort of controls problem, right? And so coming back then to the question of robot design, I think there are a lot of really interesting questions and discussions that I'm excited to have with all of you on, well, I think in engineering, we've have a pretty good handle on how we can design things with very specific specifications. But when it comes to embodied intelligence, well, the question of how do we design a robot's body to simplify its control or to enable it to perform desired behaviors more efficiently, how do we take that and turn them into some sort of design objective, or how do we think about this in the context of the robot design problem, I think is still wide open and very interesting. So that's my overview. A lot of this work was done by my lab members, who you see pictured here. And I'm excited to talk with you about these ideas later in the panel discussion.
Thank you so much, Cynthia. Some very interesting ideas. I was just wondering, because you presented this lovely framework for design, I just wondered if you just had any quickly thoughts on the role of simulators for such of this design. So you talk about computational design for these structures. Do you approach this from a simulation first, or an intuition or bioinspiration approach?
Yeah, so for us, we do it a little bit from both sides because, like I said, it's very difficult to figure out what is the real objective that we're trying to satisfy, right?
Yeah.
So we do use simulations, and we do think about, well, if I have a robot and it's a graph, how do I compose the parts of the robot together? How do we provide theoretical guarantees? But at the end of the day, the success of those computational approaches relies on the ability of the human who programmed the system to very clearly articulate what is they want the result to do,
Yeah.
right? And so this is related to the plenary we just had, right? So
Yeah.
if so, we try to tackle it from both sides. On the
Yeah.
one hand, trying to figure out what is it that, how do we describe what is it we want the robot to do? And then on the other hand, assuming we have that objective in place, how do we get a computer to help us design the robot?
Thank you very much. I think that'll be something interesting to discuss more in the panel discussion. So thank you very much, Cynthia.